We are in our Q&A session. I'll turn the energy back up. Everybody get excited. So questions for Taylor A. Cisco Jr., please raise your hand in Zoom using Option Y on Mac or Alt Y on Windows. And we have a ton of comments. Rick has been posting notes, but it doesn't look like those are questions. Yeah, so it looks like these are basically just notes in the chat. So I would say, look at that. Got 3 hands that went up immediately. Let me go to Bill Alec. He was first. Bill, go for it, sir.
Okay, can you hear me, Tim?
Yeah, can you turn your camera on, Bill?
For some reason, it's turned off. It was working earlier.
Oh,
and
okay.
then for some strange reason, it shut off on me.
There we go.
Start my video, okay. No.
Oh, well, yeah, don't.
Oh, well. Okay. Back in 2016, at the Extraordinary Technology Conference, I was approached by this fellow by the name of Bob Boyce. And Bob was hired to come into Area 51, and as he was hired as a tech to troubleshoot a problem that they were having with the ARVs. Okay, Area 51. And the problem that they were having, this was back in the 70s, the problem that they were having was a phenomena called inertia leakage.
Oh.
And I don't know if you ever heard about that, inertia leakage.
I'm writing it down.
But it's an inertia modification technology, on these craft. Okay. And this problem with inertia leakage is that it killed the pilots. It killed the pilots. And this is kind of reminiscent of what happened with the Bell device, back in when was that, in the 40s?
The Glock?
Yeah, the Glock. And so they were having this problem, and he told me he had to come in and fix their problem. And I don't know if you ever heard about this problem, inertial leakage.
Yeah.
So it's like an uneven field produced by their technology. I don't know if it's rotating or what they were using. I think they were rotating a field using capacitors or a network of capacitors, but producing some sort of a scalar or a Geist field of some sort. And it had this problem that it was an uneven field. And so he had to come in and fix this problem. And I don't know if you ever heard of inertial leakage or any sort of thing like that.
Well, it's interesting. I mean, my feelings are that in the diagrams by Mark McCandless, you had that stack of capacitors at the base of the ARV.
Right.
All right. Now it wasn't just like a stack of pancakes. They were sliced up. Okay. So it was like they had little pie slices all the way around that stack, or on their so-called lifter stack. And it implied to me that they might use one slice with more voltage or more current to alter the thrust as opposed to another slice. And so that would enable them to, go to the left or go to the right, that kind of thing. And that slippage might be between those pie slice condensers, because I imagine with that kind of voltage and the precision that's needed, any slight mistake can be devastating.
Right. Exactly.
But very interesting. I had never heard of inertial leakage, but I have it on my notepad.
Well, this was a problem they were having back in the 70s. So
yeah,
maybe they fixed it since then.
Well, and Bill, let me preface that by saying that's a claim, right? We always want to preface, that's what he said, because what one of the things,
prove it.
Yeah, and but unfortunately, I think that's this area, right? Especially when you get into anything related to UFOs, is like levels of reality, and none of us know. We're all just kind of, and then it becomes, okay, what does one person think is credible versus what another person does? And a lot of that's like storytelling. So I don't know.
Right.
But well, thank you, Bill. Let me go to Morgan Lynch next, sir. Morgan looks surprised. I think I went too fast.
Can you guys hear me?
Yes.
Okay. Yeah, sorry, I had to unmute. Okay, so I missed the first half of this presentation. I just got back home. But I saw a couple things which made me very interested, actually. So the idea is that you are having magnetic monopoles that are superluminal. So my first question is there some sort of symmetry operation of Maxwell's equations which can bring you this? Is there something I can do to Maxwell's equations with some superluminality somewhere that I can get a magnetic monopole out of this?
Well, the work that I've seen primarily by Rakami and Keith Fredericks is that the work is done with the actual special relativity and with the combination of what's called a Coulombic flip, for example, along with the reinterpretation principle. They have geometric consequences in terms of looking at and identifying a particle itself. Now, in terms of the particle generation, how one gets the actual charged tachyon, I couldn't address that too well. I mean, people like Jacques Consiglio, theoretical physicist, and Giovanni Moldinese, they're the ones who are, so to speak, playing around with that, okay? And in their writings, I don't see the word Maxwell too often, Okay. A lot of stuff they do is quantum gravity and this stuff, good for a nosebleed in terms of the math.
And then, so if I have a superluminal particle, magnetic monopole, some sort of charge going on there, is there any implication about vacuum Cherenkov radiation? Do you know of any predictions that this would make?
What kind of radiation?
Vacuum Cherenkov. So I have a charged particle traveling faster.
Oh, okay. Rakami indicated that in detecting and dealing with the particles, Cherenkov radiation wouldn't be a factor. It wouldn't be something that one would use, all right? Okay. You have the Cherenkov effect. Again, you have something, well, I'll get into it, but bottom line, Cherenkov radiation, the so-called, I think it's called X-wave radiation. If you have solitons, you have a bunch of things acting together, their speed might not be above the speed of light, but the way the waves occur amongst them, the way you might say the peaks, propagate across them, that might be superluminal, So he lumps things like the Cherenkov radiation, the things like the soliton type phenomena in the same category. It's not a factor that one deals with when handling, detecting that kind of stuff, the actual particle, the actual tachyon.
Okay. You had mentioned, this is what caught my eye, was you had mentioned Leonard Parker's work, and he was at Milwaukee. That's where I did my PhD. I pulled up his paper really fast. And he had mentioned, you'd mentioned and Parker had mentioned that if you have photon-photon scattering. So if I have a strong electric field, I can have a photon scattering off the electric field, and there you get twice the probability if there's tachyons present for a certain type of interaction. Do you know, is there anything you can comment on that? Is that something you know a little bit more about in terms of a signature for strong field QED of how you can confirm this?
I don't. With the photons, no. I mean, some of the stuff I read has been going back to the capacitors, so-called capacitors, like the setup that Podkanov has. Okay. High energy density, the superconductivity, those kind of factors. Okay. In terms of the photon scattering or photon tachyon scattering, I haven't seen too much about that. I know with the Podkanov experiment, they cross beams.
Yeah,
okay. You have the tachyons crossing the photons, and the photon beam is attenuated when the pulse goes by. Okay. All right. So there's a clue there showing either the photons are scattered, or well, I'm kind of old. Okay. So when I say scatter, I shouldn't say it like, no, I'm in my 70s. I'm not quite 80 yet. So, for me, scattering means collision, the old fashioned way. Yeah. As opposed to, fields interacting with each other. So bottom line, the tachyons manage to perturb the path of the the photons from the laser.
And you said, was it Pomkinov? Can you spell it Pomkinov? Can you spell it really, like, so I can find a reference or something?
I might be mutilating it. This name is spelled Podklevt.
Okay, that's way better than what I thought.
And it's two of them. It's like mutton Jeff. It's Podkinov, and the other person would be Giovanni Moldenisi. The Giovanni is Giovanni, and Moldenisi is as it sounds phonetically, M-O-D,
Okay. And then, okay, so again, sorry, thank you for answering these questions. In your abstract for the talk, you had mentioned Bruce Maccabee's hypothesis. Can you tell me what this hypothesis is?
UFOs generate magnetic monopoles.
And that's how they're generating thrust.
Well, that's the A rationale. All right.
Okay.
The bottom line, when you look at you missed the good stuff in the beginning.
Yeah, no, I came in
bending and all that. Well, you'll see it on the rewind. On the rewind.
Yeah, no, I'm going to see this, but it was the Parker reference that got me. So that's why. Yeah, no, I apologize for showing up late. So okay, so I'll go back and I'll do my homework. But okay, yeah. So yeah, sorry for showing up late, but thank you so much. That was I caught the last bit of it, but I'm hooked from just that.
Now, all this is coming out of a paper.
Oh, which paper?
So my paper is on academia.
Okay.
.edu. And the title of the paper is the title of this presentation.
Okay.
Magnetic monopole clues, propulsion clues.
Okay, same exact title?
Yep, exactly.
Okay, I'll look this up. Yeah, thank you so much. This is very, very interesting stuff, actually. Yeah. Thank you.
Awesome. Well, and thank you as well. So before I go to Jared real quick, I just wanted to mention something. This is just something I've been seeing, and I've had to do my own research on this. So I thought I would share and save you guys a little bit of time. So I realized not too long ago that I do Zoom now I do this conference, right? And then I do like 7 or 8 Zoom meetings a week for work. And then I'm doing the interviews too. And so I realized that I'm basically screwed when it comes to Zoom. I'm never getting away from it ever, right? Like this is like the 7th level of Zoom hell. And so I figured, okay, well, I'll break down, and that's kind of the reason why I have a little bit nicer setup now. So the thing I'm using, I'll paste this into chat. If you guys are interested in this, I bought, it was about $100. I got it at Best Buy. It's a 2-foot ring light. And you can turn the intensity up and down. You can also change the color. And this thing comes in, actually for $100, it's pretty handy. I would say this is one of the few things I bought that's actually kind of worth the money. So I'm definitely using the ring light. The other thing I'm using, and this is so handy, is Logitech Zone. Now, a lot of people like Jeremy Reese, he has a professional podcasting studio. So he has a really expensive mic and all of that stuff. The problem with a lot of those setups is if you have echo in your room, like my room, this room focuses the echo on me. And so I actually went out and bought a $400 mic, and it was horrible. So I used the Logitech Zone. This is like a $100 headset, but it's noise canceling also. And so, if you guys end up doing a lot of Zoom stuff, the ring light and the headset, these aren't the prettiest, This one has a cord so that I can do 6 hours without having to charge it. So this is kind of old school, but these have been well worth the money, So let me go to Jared next. I should apologize for interrupting you guys. I thought I would just share that. I'll put links in chat here. Jared, you ready, sir?
There we go.
Sorry about that.
No, you're good. You're good. Excellent talk, Taylor. That was very interesting. I got a couple of quick questions and then a couple more in-depth ones. Do you have a contact or an email or a website where we can try to get in touch with you outside of this?
Yeah, the email is my full name. So it's like Taylor, got the T-A-Y-L-O-R part. The middle name is A-A-R-O-N, Aaron, and the last name is Cisco, and you tack on the end JR. So it's Taylor Aaron Cisco Jr. at yahoo.com.
Excellent, thank you.
I passed, and let me just compliment you on your TRB3.
Thank you. Yeah, I had a talk a few weeks ago here about it. And actually that's where one of the questions I'm going to be going to is the stuff that I found that may be making that fly may also be related to your monopoles. I do want to find out the MUFON report number, if we can get that from you for the, at the very opening of your talk, you were talking about the gal that had filed the MUFON report for the magnetized trees, I think it was.
Oh, all right. No, you said girl. All right, there are two ladies. One was the music major, so to speak. I mean the one in Florida.
I think so. Yeah.
Driving home. Okay, in my paper, if you go to academia.edu, in my paper, the one by Maccabee says, you know, strong magnetic field from trees, something like that. But you'll see, if you see Maccabee and magnetic, you know, that's the paper. He even has a nice diagram, cool, you know, drawn by the witness. And it's kind of cool. It's a little, I don't know how comfortable you are reading through the weird data, you know, with the magnetic measurements and that kind of stuff, you know. And I tried to convert the readings from Cornet's book over to the units that Maccabee was using, the nanoteslas. And I got kind of tangled up with some stuff, you know. There were other things I was looking at that that Dr. Maccabee did I didn't quite understand, so I didn't touch it. But it's a good paper, and bottom line, it had been read by different people, but no one ever cites it. That's the weird thing.
My next one is, when you're talking about bending, shaking, twisting of the trees, I find some interesting overlaps between that and crop circles, but differences in complexity. So the crop circles have like very specific scanned aperture, like radar style ability to draw pictures with, if it is magnetic monopoles that is causing the bending or the twisting of the stalks, the reeds of the plants, and the crop circles, as well as these trees. If it's the same thing at play, it would seem like the trees being bent over is just from a generalized, you know, strong lift, whereas they're able to use it in a much more fine-tuned way to actually like draw pictures with it.
Well, from what I understand, from what I understand about crop circles, all right, the vegetation itself, the degree of moisture in the leaves, the weeds, twigs, whatever has been bent over has been changed substantially. So it seems like the reason why the pattern is placed or in place and remains is because that moisture has somehow been changed, evaporated, or whatever. So it stays in that position, apparently grows that way. With the trees bending and such, also too with back to the vegetation, in dealing with the moisture, there might be an implication that something's being heated or boiled, you know, with microwave type stuff, all right? With the trees, on the other hand, they are just bent over. Give you an example, all right? So if you imagine a tree is being bent over by this, let's say by your TRB3, all right? This thing is bent over, right? And you look at it. Now, based on the reports, the leaves aren't flying off. Okay, so maybe at 2 or 3 G's of acceleration, the tree bends over. I don't know how many G's it takes to take a leaf and pull it off of a branch from a green, you know what I mean? So here's this force field doing this, but there's no debris. It's just a tree doing its thing, the leaves going with it, thrashing around, making noise. All right, so I think there's a whole different force at play, going back to Plotkonov's thing. Even when you look at the thing by Burkhart Heim, they have this field, all right? But it's a field, so you figure that if the tree is going to be bending in the field, loose stones and nearby rabbit are going to be in the air also flowing with the flow. So I think they're two different mechanisms.
That makes sense. And my last thing, so with my research, it it was a lot to do with the Schwinger effect, and when you exceed the vacuum breakdown voltages or magnetic fields, you can start getting pair productions of electrons and positrons. So from some of the papers that I read, it sounded like you can also produce magnetic monopoles when you exceed the Schwinger limit. Also, you can produce tachyons when you exceed it. The reason for it may be because you are creating negative permeability of space-time, which is folding of the space-time, which now is allowing you to propagate particles through it faster than light. As for the monopole side, I don't have any answers on how people are saying that exceeding the Schwinger effect gets you monopoles. The papers that talk about that are somewhat vague. I was wondering if you had any insights.
All I have are feelings. Now, what I find is so interesting is that nature has a thing for pair production, right? You have Cooper pairs and all kinds of stuff, but you know, there's this obsession with pair production, I guess to conserve momentum or something. What seems to be interesting with that, like with the Pogkanov, you know, impulse gravity generator, you have a fast component, then you have this slower one that dies off quickly. And I got to reread Giovanni's paper again, but it seems like if you multiply the velocity of those two particle beams, the product is less than the square of the speed of light. All right. Now for Giovanni Moldedisi, if it's beneath like something like 86%, there's some number, but if the product of the two velocities is less than like 86% of the square of the speed of light, you cannot violate causality. It's a way of saying, no, you're not going back in time. But I think the path that you're following could be pretty productive, actually, you know, because it's all about taking poor little space and squeezing stuff out of it, you know, because we have that the vacuum quantum fluctuations. It's not understood, and I think what we're doing now with this stuff is squeezing things out of it. We're perturbing it, making it produce things for it, and the poor baby's got to produce in pairs. The weird thing too is that the data that Keith Fredericks has, the pattern it's following is of the old-fashioned Bohr atom. The quantum levels are larger, so to speak, you know, but it's that same old formula. And that Bohr formula was based on orbits. And, you know, electrons go in shells or clouds, right? But yet you're still dealing with this thing that surrounds us, the so-called quantum foam. So I think there's something to the pair production, and you know, so I would encourage you to keep on doing your research. Can I ask you a quick question?
Sure.
Now, have you heard of any effects from the TRB, so to speak, that do things like stop cars or power systems?
So one thing that is very important with the TR3B, that's a reproduction at best. The flying triangles have been observed since the late 1800s. So if there are examples out there where they are stopping cars, we might find them in the 20s, 30s, 40s even, where it is definitely not terrestrial tech that's doing it. The angle that I went through was the terrestrial side. Aliens or extraterrestrials or whoever had the ability to make these black triangles before the Wright brothers, right? Their methods would be so likely be very different. The only thing that comes to mind is they're often found near nuclear power plants. So I've had some people reach out to me in the last few weeks saying, hey, here's some pictures when, you know, that I took of it. It was just a couple 100 feet above me and it was hanging out right over this nuclear power plant. But not like the stories of the saucers where they're leaving actual magnetic swirls in the metal of the car, right? Or people are removing all of the copper out of their car because, you know, magnetic reasons or whatever. No, it doesn't seem like the black triangles, generally speaking, are being referred to in that way.
Yeah, I think the propulsion system is different than the things that produce magnetic monopoles, you know. So there are different ways of flying. You know, we got propellers and jets and ramjets and turbojets. So I guess ET, whoever has their own things, you know, their own variety of fuel or whatever thrust producers.
If I can just put one final addendum on that, it seems though that any stories out there of any UAPs where you see different colors of lights coming from the edges may be an aspect of this birefringence of the vacuum, this alteration of the speed of light going through the vacuum. Just a hypothesis I'm working on, but it's definitely something to keep your eye on with regards to any of your researches, is whenever there's colors involved and they're not, you know, blinking light colors, but they're, you know.
Interesting. Good question.
Thank you.
Wonderful. Okay, well, thank you. And so let me go to Harold Tabarez next. Harold, sir.
Hey, great presentation, Mr.
Thank you.
Taylor. Great presentation. That was good. So my question has to do with the point that you brought about the trees, you know, curiosity that there may be magnetic monopoles on the top of the tree. Now, granted that if the UAP is creating a fast spinning magnetic field, it will obviously magnetize a tree, especially if it's a very high intensity, the same way we make magnets, you know, by spinning, you know, by putting a high current, you know, etc. Now, my question is, how do you make a distinction in looking for the magnetic monopole that what you are detecting is not a tree that have been magnetized, obviously have been proven, magnetized, just like a magnet. How you make the distinction that what you're not detecting is either a depletion of electrons on the top of the tree, or a depletion of proton, or a magnetic monopole? How do you make the distinction in those three? Do you know that what you're detecting it to make sure that you are detecting a magnetic monopole?
Well, I think, well, for one thing, if you're measuring the field intensity, does that intensity vary with the inverse square of the distance? Okay. If there's a variation with the inverse square of the distance, that means it's one polar, right? Either North Pole or South Pole. That's why it's inverse square. So that tells you right up front, you're dealing with something that's different, getting in the magnetic monopole area. The observation that Bruce Maccabee made was at the top of the trees in Gulf Breeze, Florida. They had a strong magnetic field, but after a week, it was gone, okay? With ferromagnets, you know, if you magnetize a bar of iron, it stays strong. It doesn't weaken, okay? And so this phenomena with the wood, and technically speaking, wood should not be magnetized. Maybe you can shoot particles into it, like, you know, bits of iron filings and paint it or what have you. But the actual wood molecule, the fibers, the animal cells that make up the wood, those things aren't magnet. They're neither ferromagnetic nor diamagnetic. You know, they're just like a piece of paper when it comes to the magnetic field. You can pass stuff through it, and technically, you know, the field is not deflected or influenced by the presence of the wood or the paper. But yet, like with the tree in New York at that Jewish cemetery, that tree is above a strong magnetic force. That tree, to my knowledge, still retains a magnetic field, yet that theoretically is impossible for the wood fiber. You know, and I see somebody here is asking, okay, well, the thing is that the issue with anything dealing with a question came in about the water. All right, if you have trees, okay, they have sap that's moving through them. Now the sap moves slowly. So I wondered sometimes if the magnetic monopoles are somehow trapped, going so fast between the variation of densities between the sap and the other fibers, okay? because of that nature of the molecules. But the presence of water really wouldn't have much to do with that. Now, if you try to induce a electric field or magnetic field in a tree because of the water, the tree just might heat up and blow apart. I mean, that's how trees blow apart when they hit with lightning. It's not the fire, so to speak, that makes them blow up. It's that water being turned to steam. If you're seeing a film of a tree blowing up, you see, you know, this steam explosion as opposed to dynamite going off or flames and that kind of stuff, you know. So the one thing is that with the trees, they shouldn't be magnetized at all. So one trace would be the inverse square law. Another trace would be if you take it over time. If the tree is the only thing out there generating the field, like in Gulf Breeze, Florida, or like in the other case with that UFO crash in South Haven, over time the field gets weak. Okay, so that means you had something that might have been influenced by trapped magnetic monopoles. Now, Keith Federick's work tells us that magnetic monopoles can be temporarily trapped. You know, those particle tracks in photographic emulsions are the remains of a magnetic monopole going through there for a while and eventually decay, being absorbed or whatever. So there's a trace, there's something left. And so maybe if someone could get up into the trees and take samples and look at them with a good microscope, they might see something that might resemble what Fredericks has captured, you know, with his photographic process. A good question.
Oh, thank you, Dino. So what would be the specific signal? Let's say you have your device and you say, aha, I have a magnetic monopole right here that you're not detecting. For example, the tree is magnetized like a magnet. You have a north pole and south pole, but instead, you know, let's say if there's excess of proton on the tree, you might say, okay, well, it has the protons or excess electron, you know, just like a generator produces electricity, you know, that moves the electrons in the wire. What is the specific signal in your device that would say, aha, here's a magnetic monopole exactly?
Well,
that
I think
will
one thing is
distinguish whether proton, electron, or magnetic monopole.
I think one thing would be the charge. Is it north or is it south? Okay. Now I'm seeing a post on the screen here too about different fluids containing, you know, iron or ferromagnetics. The issue there is that their presence can distort the Earth's magnetic field, right? Now the question would be, can there be enough material in the sap of a tree to generate the distortions that were measured by Maccabee? Again, his estimate was that the field being produced, the distortions produced by the top of the trees, was equivalent to having a destroyer parked up there. Okay, that's a lot of iron in that tree. Okay, so maybe you can have iron filings floating about in the sap and that kind of stuff, but you got to have so much that you can detect it. Okay. And these are people using metal detectors outside the tree, having to notice that the strength of the field is coming from the top of the tree. You know, so the concentration, so the fact that this inverse square relationship, that's a strong hint. I think magnetometers, if I'm not mistaken, they don't detect polarity, they detect field strength. So if you have I forgot what the device is called for measuring that kind of thing, but if you have a so-called magnetometer that can tell you the pole, if you're looking at North Pole or South Pole, that kind of a vector, that's saying it's only, you know, one pole as opposed to several, you know, two poles or what have you. But the fact that it's inverse square and the fact that it's just that one charge, along with the time variation, would let you know that there's something happening. But also just the fact that it's a tree and the tree is giving off a signal like a battleship or like a large chunk of iron. That alone lets you know there's something that needs to be examined, you know.
Have there been any examination when you have the magnetic field, you know, there's obvious a lot of conclusion about that there is an actual magnetic field when UAP gets close to matter. But is there any studies about the relationship, the electric field, the intensity of the magnetic field when there is a magnetic field, like for example, in the top of the tree? Any conclusion? I mean, the square load is obvious, but what about the electric field? I don't hear much about creation of an additional electric field when you have that magnetic field induced by UAP on top of a tree.
Now, I don't know. I would assume that electric field on top of a tree, one, it might be easily neutralized because it's on top of a tree and there's stuff out there in the air. One. Number two, if it's moving, you know, a moving charge, electric current generates a magnetic field. So having a charge in the tree for it to generate a, you know, a magnetic field, it's got to be moving somehow. There's got to be some sort of a current flow occurring there. And again, we're talking about something that's strong enough to register a field strength, say 3 times the Earth's background. Okay. I'm trying to think here. I believe that the distance, for example, in one of the measurements made by Maccabee between the end of the magnetometer and the tree tops was like 10 feet. Okay, and they were getting that, I think, at like at that distance there, a pretty strong reading above the Earth's field. Okay, in terms of like directly beneath the tree, and measurements when they were 20 degrees off the tree, you know, looking up at, you know, measuring 20 degrees from the tree itself from the top down, you know, they were still getting a good reading, and those distances are pretty sizable. And again, magnetic fields, they drop off rapidly, inverse cube. Okay, inverse square doesn't drop off that rapidly. So for it to be, you know, still detectable at a range of like 10, 20 feet, you know, it's pretty strong. And things like, you know, again, like the iron filings painted on the tree, dumped on the tree, you got to have enough that's equivalent to a, you know, a destroyer, a naval destroyer. So the fact that the tree has it is a strong field. That in itself would be a clue that you might have something that needs to be investigated.
Awesome. Okay, well, thank you.
Thank you. Great explanation. Thank you.
And Tony is writing in chat that your blood contains iron too. Tony, I contest that. My blood is completely coffee. I have replaced it with coffee completely. There's no iron in this blood. So it doesn't last very long though. I get about 4 to 6 hours and then I have to refuel. It's terrifying.
Does your blood deflect the compass? If one walks by you with a compass, does the needle point at you?
I'm not sure. I'm not sure. Can you magnetize Starbucks? I don't know. I don't. Let me go to Mr. Michael Boyd next. Sir?
Hello, can you hear me okay?
Yes.
Great. So I'm curious about, you're talking about tachyons, and I'm curious if, would you be aware of what's called quantum tunneling, the phenomena quantum tunneling?
Yes, I had a class a long time ago in quantum mechanics, and that's how we were introduced to it, you know, that tunneling to a potential barrier.
So in quantum tunneling, would you consider that quantum tunneling is superluminal?
I've never heard it taught that way.
Well, I mean, it's instantaneous, so it's going across some distance of the barrier, and it's doing it instantaneous, so it would have to go faster than light, wouldn't it?
If it's instantaneous, I don't know. Are you sure it's instantaneous going from A to B?
Yeah.
Or is it quantum entangled?
Well, sort of. That's quantum entanglement is the same thing as quantum tunneling. So it's a superluminal effect.
Could be. I don't know. It's a good question. I mean, I know one of the great sacred rules of quantum entanglement is thou shalt not exceed the speed of light.
That what?
thou shalt not exceed the speed of light. You can't consider that in trying to handle problems in quantum entanglement.
Yeah, well, quantum entanglement is basically the opposite of that. So, so would you consider that this is a so-called tachyon interaction that's going on here?
I don't think so. I haven't heard anybody tie tachyons to the quantum tunneling.
So now that when you're talking about tachyons, then you're talking about, say, between our star and another star. It's, you were using an example of basically that essentially instead of tunneling into a barrier, you're tunneling away from the barrier. Why couldn't you go both ways? Why couldn't you go both ways?
Now, the difference between quantum tunneling, though, between what we're talking about, is that at A and B, in quantum tunneling, when you're going from A to B, the intensity at A is greater than the intensity at B. Okay? The wave equation diminishes in intensity. Now, with tachyons, like with Podkunov's tachyons, they don't attenuate. You traveled at 1,211 meters, and it's still the same old. It's the same old strength. So tunneling wasn't involved there.
Well, I mean, isn't it basically you're sending information between point A and point B, and in one case it's interacting with matter, and with the other case it's not?
Well, again, like quantum tunneling, that old potential barrier, right? And so
right. Well,
you're paying a price for going through it. And there's no so-called potential barrier with the tachyons. Nothing obvious, because they have sent this thing through walls. They've sent it through walls to hit targets and hit piezoelectric phones and all that stuff. And the weird thing is that there's no attenuation. What starts, what ends is at the same level.
Well, I have some data that if you wait and watch my talk, I'll show you some data that would suggest it's different than that. It has to do with the presence or absence of matter.
Okay.
Okay. And I appreciate your answers to my question. Thank you.
And I enjoyed your presentation earlier about considering the role of the coronal mass ejections.
I'm going to talk about that a little bit too. So.
Yeah, okay. I enjoyed that line of questioning you had in one of the earlier presentations. It's pretty cool.
Oh, and for information, everybody's information, it's not just Apache. I have 4 government UAP videos that I'm going to be going over: Apache, A10 Warthog, La Bruja, and Rubber Duck.
Well, the last 2 I don't know about. The Apache and Warthog are my favorites.
Yeah, Rubber Duck and La Bruja are what's cool about them is they're both cold in the infrared.
Now, going back to quantum tunneling, since you brought it up, I have a license to address that, okay? Since you brought that up, the fact that it's cold, isn't that interesting?
Yeah.
Because with Burkhardt-Himes theory, you have all this stuff happening, and they blame it on the way the so-called gravitational waves of his theory interact, and that's why it has this endothermic effect around the device theoretically. All right. The neat thing with the tachyons, Podkunov tachyons, is that here it's going through a target. It causes the target to experience 1,000 Gs, which is this unheard of. But the baby's not hot.
Well, maybe it's the cooling process that has something to do with the 1,000 Gs.
Well, it's either the cooling process or the way they don't interact. It's a different kind of interaction. It's like information. The particle now, it says move and it obeys, and I guess it crawls against the quantum foam or something and obeys. I don't know, but it's an interesting interaction sequence, and the fact that there's no heat going along makes it very, very fascinating.
Cool. Thank you.
My pleasure.
Awesome. Okay, let me go to Eric Hermansen next. Sir?
Hello, how are you, sir?
Fine.
Oh, good. I'm sorry that I missed 80% of your presentation. I tend to forget everything on a Saturday, so I was late. But first of all, I'm very impressed. You're a very knowledgeable person. I'm curious if you are a physicist or your background is physics, perhaps educational.
Well, to address the first part of your question, okay, I'll be 78 in December. So I've been around a while, reading things, collecting things, that kind of stuff, okay? So I wound up reading a lot of stuff, all right? Now, my baccalaureate degree is in physics, and I have some graduate hours in theoretical physics and the math that goes with it, okay? I made a mistake, unfortunately, and in proving or in examining my advisor's dissertation, he guessed on a certain phenomena he was measuring, all right? And so I went ahead and examined it from a theoretical physics standpoint and found out that when you look at certain terms in his guess, they're all imaginary, all right? Which means they can't be measured. It's a nice way of saying, well, it's a neat property, but there's no fruit in pursuing it any further. It's just a mathematical coincidence. It's like Bode's law, the way the planets are arranged around the sun. So far, to my knowledge, there's no explanation for Bode's law, though the mathematical pattern works, okay? So I've had an interest in this stuff for a long time, and I collected a lot of stuff, you know, so I think the turning point in my life was seeing Star Trek, the first movie. And unfortunately, it actually made me cry. I was so embarrassed in the theater. I actually broke down and cried when they showed the Enterprise and Doc. And that's when I realized that my love for space drives and that kind of stuff was stronger than what I ever imagined. So I went back to reading, you know, journals.
That's
you know,
excellent.
theoretical physics journals. That's why I went back to it, you know, so I wound up reading all that stuff. And I was burnt in high school, so to speak. I don't say burnt, but I blew a lot of time with the Dean space drive. I was in rockets, got heard about the Dean drive, and spent a lot of time exploding gyros and all kind of stuff, you know, trying to shake force out of something. But when I went back after Star Trek, you know, then I found out that the things I had heard about the Biefeld-Brown effect were false. That when people did the replication, they didn't do it correctly. They didn't do it specifically. They didn't repeat the actual experimental setup. They did abbreviations and what have you. So, but stuff happened, you know, and so I'm just very, very curious. I'm glad to see young blood in all this. We got to have some young, energetic minds that can blow some time and genius on some of these metrics and math and what have you.
Well, and Taylor, let me jump in, and I know I'm taking things out of order, so I owe an apology to Gerald. I want to try, before we get to the top of the hour, I want to try and squeeze Mark Sokol in. You were talking about the young genius. Mark is up there. Mark actually is working on a device to create a magnetic monopole, and so I wanted to have him demo that for you. And you know, we only have a few minutes left, so. But Mark, let me go to you next, and again, let me apologize to Eric and Gerald because I'm jumping around.
Oh, okay. So I don't know if this is what you meant by a magnetic monopole, but we're trying to create over here is a radially magnetized field. So it would be south in the center and north on the outside. The way we're doing that is just a whole bunch of iron. It's shaped. There's a iron rod in the center that's machined to go through the center of this ring magnet. And then there's just iron all around. This is a ring as well, and there's an electromagnet inside of it. Powering this entire device or pulsing it with a large nickel metal hydrate battery from the battery shop that's on the other side of the shop. During your presentation, we're actually charging up the battery because it wasn't fully charged. We did successfully make a monopole earlier, but we're only pumping 80 amps through the coil, hoping to get like 100 this time. You will notice when I disconnect these leads over here, There's going to be a large arc. That's normal because the coil has a built-up inductance. So when you disconnect an inductor, you're going to see a large spark. So here we go. Okay. Okay, we're getting 80 amps. And there we go. It is magnetized. So just pulling it out over here. So this is basically machined so that the magnet fits in there nicely. Now with the magnetic film, you can weakly see there is a magnetic. Should be south in the center and north on the outsides. Is this what you meant by a magnetic monopole?
I think it would almost have to be, because I mean, traditionally speaking, magnetic fields don't exist in nature. It'd be interesting. Could you do something like that as a sphere, Mark?
That's the thing. If you got a whole bunch of these and magnetize them and then cut them to shape them as a sphere, you could do it as a sphere. Yes.
And that would effectively be a monopole. I mean,
that would be a true magnetic monopole if you can do that. But
I think the thing is that if it's a monopole, there has to be just one charge, either one north pole or one south pole.
Yeah, he would be hiding the pole. He would be hiding it from
a monopole is like scalar. It means that it's it versus the outside realm, but it's also it versus inside of it. So if you have a magnetic monopole that's, say, this big and it's south on the outside, there's going to be north in the center of it. But from its point to the rest of the universe, all we see is the opposite polarity. So this is actually based on the Manelis device that we're working with Aidan Schaffer, who I believe is here as well. We've been working on this for the past couple of weeks. So it's real serendipity that you showed up with this exact presentation right when we finished this device and got it going.
I mean, have you put iron filings around it to see what happens?
Around this magnet?
Yeah.
Well, we have magnetic viewing film that shows.
Well, yeah. I'm just curious what the filings would do.
Yeah, your film.
No, we're trying to keep clean. No, it's a clean area. No iron filings. But thank you very much.
We could put a plastic.
There's a clean area. No, we can. But yes, that's a good idea, Eric.
Okay.
But,
Okay, Aidan's vetoing that, but maybe we'll put the iron filings in a bag or something to keep it clean.
And I'm always open to things that explode. You know that, Mark. If it explodes, I'm open to it.
Oh, this part does explode. You saw that flash?
I did, but there was. Look, it's fine. You can reuse it. There's nothing broken. I want like explosions.
Also, Taylor, you were talking about the pod clamp impulse experiment. That's something that we actually are working on replicating with the vacuum chamber and everything. We already have the vacuum chamber here. The cryogenic glue alone set us back $1,200 just for the glue to get the cryogenics into the chamber. And we're waiting for Todd Desiato to come up from North Carolina with our high-speed camera so we can film it at a couple 100,000 frames a second before we go for that one. But we are planning on replicating that experiment in the near future. Hopefully by the end of the summer, we'll have it done.
Mark, I didn't realize you guys had that. There are so many things you could film. If you can do a couple 100,000 frames per second, there are so many different experiments that you could film.
Yep. Yeah, including Ted Pittman's device that he was on here a couple weeks ago. His device needs to be filmed in high speed, and I promised him a couple hours. We're going to come down to his lab right here in Brooklyn, and we're going to film his device in high speed and try to slow it down to give everyone an idea exactly what's going on.
We could do high speed footage movie night. I mean, I don't really have a life, so for me, that's like,
Well, you can do the editing because I heard that's a lot of fun.
And once you have a high speed movie night, you really don't have a life. I mean, that's the cutoff. I'll never date. That's the way it'll work. So what'd you do last Friday? High speed movie night. High-speed footage of spark gaps. So, okay, well, so yeah, we're just about at the top of the hour. Eric, were you all done, sir? I want to try and squeeze Gerald in really quick too.
Well, I guess I'll hold my question for later. I just wanted to mention to Taylor that the DoD already demonstrated stopping car engines in 2018. If you look in the chat, you can find the link for the video.
And during World War II, the Germans had something for that too. That was the story I'd heard in the Rhine Valley. That's
really
that's pseudo mythology, but supposedly they were doing experiments in the Rhine Valley, and one of those was trying to transmit electricity through the ground using resonant frequencies. Not Tesla stuff. There was Zenith surface waves, I believe. And then another thing that they were doing there was they were trying to stop the engines of Allied bombers. And I think they used a couple different ways. One of those was electromagnetic. And I think the other one was actually, they were trying to like bulk add something to the air that would foul combustion in Allied bombers.
Okay.
So, I might add that the one thing that's different though, with both of those approaches is that the target is damaged. Once it's been turned off with those electromagnetic pulses, it stays off, okay? When the cars are stopped, airplane engines are stopped by a UFO, when the UFO leaves, those devices resume operation without any hint of being, perturbed magnetically. Very, very, very few cars ever have had their magnetic signatures changed. The hood of the car would ever by that encounter. So there's a difference between doing it with the conventional magnetism, but to stop this current, the leads are melted down, God knows what happened, but there's damage done, so it doesn't come back on again when the field is turned off. But the UFOs, somehow it stops, and when the UFO's gone, it resumes operation with no clue of it had been stopped.
Yeah. Well, let me go to Gerald really quick, sir.
Thank you. Thanks for the opportunity there, Tim. I appreciate that. And I want to thank you, Mr. Cisco. Your presentation was amazing. I have two really quick questions. One of them being, would a magnetic monopole affect antennas in a Wi-Fi system?
I would assume that just the fact that it's a little ball of magnetism, so to speak, a magnetic field, all right, on a particle, the fact that it's moving, if it's going through a conductor, that alone is going to have some sort of electrical effect. Now, the specifics, that's something else. But normally a moving charge, a moving Coulombic charge, or a moving magnetic field induces, electromagnetic force. So I would assume there'd be something happening. Now, what the magnitude is, that's for the math and laws of electromagnetism come into play.
Okay. One quick comment and then my last question. The comment is, for 78, I can only hope to look as young as you when I hit that age. Good for you, sir.
So an old man in a young world.
So my second question is, I work with open core coils. They're based on geometrical magnetic vortexes. So I'm just trying to visualize a monopole. Now, I've observed some anomalies, with these coils that I deal with. One of them being, I can concentrate a north pole in the center shaft of the coil and a south pole on the outside of the coil, and then I can hit a button and flip the poles. So my question is that related to a magnetic monopole whatsoever?
In my estimation, I would say no, just by the fact that you have both poles. Now you're twisting the field, okay?
Okay.
You're twisting, it's like what the sun does. The sun has all this power and energy, so it'll twist the plasma. And sometimes when it snaps, you have a sudden reverse in polarity. You have stuff happening inside the sun, certain currents where polarities are suddenly reversed. It's real fascinating stuff there also. But I think when you have two poles, the fact that you might bring them together or, like turn them around like a rope, again, looking at it from the standpoint of field lines, like one person says there, plasma physics, that's something that comes into play. You know, the way you manipulate the lines of force, be it in the vacuum, you know, and the way you have your geometry set up, or if it's something conveying it, like a plasma that carries the charge or field, you know. So I think it's still in the realm of conventional or mainstream physics. It isn't something that is exotic like the concept of magnetic monopoles.
Awesome. Thank you for your answer.
Okay.
Awesome. Okay, well, Gerald, thank you as well, sir. So let me do this. We're just about past the top of the hour. Next, we have Michael Boyd coming up. So I want to put this back on gallery view. Everybody, please give Mr. Taylor Cisco another applause. Sir, thank you so much for presenting.
Thank you very much for hearing.
Thank you. You covered a lot of area, and there was a lot of depth and a lot of great questions. So it was wonderful to have you here, and I would love to have you back sometime. That's, you know, that we would love to have you present again.
Okay, love to.
Absolutely. So now, though,